Hello, I'm Ann Hanks from PASCO Scientific. And
I'm Waqas, also from PASCO Scientific.
and we're going to show you the Zeeman effect and how you set it up and give you a few tips for getting it all aligned. To show you, I'll just start by showing you the source, which is a mercury lamp. It's just a tube, and it just goes down into the holder here. And one of the first things I should tell you is that since there's a wire coming up the side of the tube, it can that wire can get in the way, so you got to make sure that when you put it in here, the wire is not facing the camera. So we have mercury. It's the gas that we're studying, and when we apply a magnetic field using this magnet, we can get up to about 1.2 Teslas and 5 amps on this magnet, and that causes the spectral lines to split. So that's what we're going to be looking at. And the way we get the spectral lines is with the optics here. What we have is an interferometer. This is a Fabry-Perot interferometer right here. And I'm being careful not to touch anything right now because I actually aligned this before we started, which most teachers do. I was reading somebody's instructions for their lab manual, and it said to the students, "This should be set up for you. Try not to touch it," which is not good. I mean, you should be able to touch it. So in order to get the interference pattern, we're picking out just the mercury green line, and there's a filter right here, green filter, that's picking out that particular line. And this is a lens that is on a holder that can translate it back and forth this way, and you can adjust the tilt of that lens so that you can illuminate the camera just right. So there's a lens here, and then there's a polarizer. And the polarizer should be set on 90 degrees when you start out, and it's not. So I'm just turning it to 90 degrees. That makes the polarization be at along the line of the magnetic field over here. Then it goes through the filter so that you only get the green line, and then it goes through the interferometer. And this is a Fabry-Perot interferometer, so it has 2 pieces of glass that are semi-reflective, and they are about 2 millimeters apart. And you can adjust how planar they are using these screws here. Now, then the pattern goes into the CMOS camera here, and there is a shutter on the camera that you can adjust if you want to let more light in or less. You're best off letting in less light so that the lines are very crisp and clear. And then there's a focusing knob here, so you have to focus in on the lines as well. The trick is getting everything into alignment so everything's in focus. And I want to show you what you see through the camera, although you can remove the camera and put your eye down here and look through it and see the rings as well, the interference rings. But the only reason you can do that is because the green filter is in place. You shouldn't be looking directly at the mercury. Yeah, the green filter takes out all the bad UV. So I'm going to show you what the camera is seeing. I have a workbook in Capstone, and it already has this set up so that you can do the experiment. And currently, we're looking through the camera. Are you seeing that? And it's pretty washed out because we have the studio lights on. So
Should I go ahead and flip this up?
yeah, I have made a cover just to temporarily cover this up. Get that over the magnet there. So that it darkens it enough that with all these lights on, you can see the pattern. So there's the interference pattern coming from the camera. And so what you're looking at, and unfortunately with these types of interference patterns being circular, it tends to make students think of electron orbits. And so they have to make the association that this is not the electron orbits. This is the different fringes that just depend on how many times it's bounced around in that etalon in the interferometer. So this is the first fringe, which is K equals 0, and then 1, 2, 3, 4 going out. I guess we might as well turn on the
Power supply?
power supply. Just go ahead and crank it all the way up to 6 volts. Let's go all the way.
We're in amps, so 6 amps.
Oh, 6 amps,
Yeah.
sorry. Thank you. Now, looking at the screen, you can see that it is splitting.
All right, we're max.
Yeah.
6 amps.
And I'm just going to record this momentarily, and I want you to turn it all the way down to 0 as soon as I say.
Okay.
Okay. Go ahead. Okay.
You do see it set up here. The setup is pretty straightforward as far as the order of all the elements. And as Ann mentioned, the hardest part is you really do have to read the instructions. Like one thing she had to do was check the level of the magnet as she was setting it up. And all of these are in the instructions that we include with the product. But with the level, you have to check the orientation of the magnet. You want to make sure that it's level with the optics on the track, so that we're looking at the light as it's straight on, and not as it's tilted a little bit because the magnet wasn't straight. And a couple of the other things, the distance, you do have to change those things sometimes, and especially like with the interferometer, getting that to be aligned is that's one of the tricky parts, and that's where you'll probably spend most of your time. But once you get it right, hopefully you don't have to touch it again after that.
One thing that we developed since we made this experiment originally was the ability to take a snapshot and then do video analysis. Well, it's not video, but image analysis on the snapshot. So I would probably be better off just taking a snapshot of no field and then a snapshot with the field completely on. Then you don't get some great big movie in there that is taking up a lot of memory. I'm going to open up my data file just to see if I can show the data. Because I had previously taken data. When you're doing the alignment here, as you mentioned, you need to level the magnet. And I use a protractor to make sure that the magnet is turned straight on, so it's perpendicular to the track. This magnet is locked in place at the moment, but we can turn it. And
I can show it.
well, now that we're
Sure.
just going to data that we don't have to take, we can turn the magnet like this, and there is a core that comes out, and you can look straight down the axis of the magnetic field at the mercury lamp. And in this way, you can see the light that's coming from that direction along the magnetic field lines instead of perpendicular to the magnetic field lines. And the light that comes out here is circularly polarized. So it's interesting that it's different than the other light, which is not circularly polarized. As I said, we're deliberately choosing, I just take a glance here at the theoretical page here. There's a picture. In this picture, we're showing the, let me unlock my page and make this picture bigger.
I can just delete that. Yeah, there you go.
Very good. These are the transitions. Mercury has 2 valence electrons, and so you're going from an S to a P, and normally without a magnetic field on, that gives you this 546.1 nanometer green line. But when you turn on the magnetic field, it will split out. The top level splits out into 3 according to what the orbital angular momentum of the electrons are and the spin. And then the bottom one splits out into 5. By choosing the polarizer in the direction that we chose it, parallel to the lines, we're picking out the lines that have no change in angular momentum along the z-axis from when it makes the transition. So we get the middle 3 lines. If you turn the polarizer to the vertical direction so that you'll get the other 6 lines that are on here. So let me go on and see if my picture here can replay. Oh, I'm in replay here, but I'm not certain which run I'm really on here.
We can just show the live shot of the.
Yeah. In the Capstone software, there's a video analysis mode, and when you first turn it on, it usually comes on with a measuring tool and some axes that are up there. Those are not necessary for this particular activity, so we usually just turn them off.
But yeah, the one that we do use, we're able to measure the diameter of the rings that we see.
Yeah,
so
there's a radius tool.
Right, and with that, we don't know what the actual radius is, but we can use that to do a comparison between one ring, and the ones that are right next to it, the fringe ones.
Yeah, for instance, I'm taking this, and when I click on there's 3 handles on the circle, and you put those 3 handles on the circle that the fringe, and then that will define a circle with a certain radius. It says the radius is 0.280 meters, which obviously it's not, but since we're going to measure everything in that same scale, it doesn't matter.
Right.
It cancels out. So when I click on it, it magnifies, and you can even magnify it more if you want. It's magnifying it by 2 times, and then you can zoom in and essentially find the center of that ring exactly. Then you record that radius, and then once you've moved on to where it's split, and here it comes, and you know, I'm not sure which run I'm doing here, but now you see that when I turn on the magnifier, you see how it has split into 3. So I need to measure the outer ring here. So I can put this on the outer ring. And take down what that measurement is, and then I also measure the inner ring. So those are the different energy levels that you're seeing that are caused by the magnetic field being turned on and the magnetic moment. So by much calculation, you can use these radii to calculate the Bohr magneton. And the rest of the analysis is just going through and measuring the different rings. And of course, we also want to be able to look at the other. Here's the 0 degrees. Let's see if it plays back. There.
And one thing to mention, so that file that Anne is looking at, she's opened it up in our Capstone software. This file, if you have Capstone, you can download a trial for it. If you don't have it, you can get this file just on our PASCO's website. So if you look up the Zeeman effect experiment, there's a section there to download, extra resources. The experiments tab, there's a documents tab if you want to look over the manual for it. But you can download this file with the example data and just, play back the video yourself just to see what it looks like.
So this is an example of what it looks like when there's no polarizer in the system. You take the polarizer out, and the magnetic field is turned on at this point. So you're seeing all the lines that exist. There's 9 of them. And then this is a view down the magnetic axis. It is dimmer down the magnetic axis through the core. And so you don't see as bright of a... That's not too bad, I can see. And when you look through that, then you're supposed to rotate the polarizer to show that it's circularly polarized, because it doesn't affect it. Okay. Any questions out there? Any questions, Waqas?
Fred's taken. Okay.
Huh?
No question.
Okay. So just a final note about how you set this up. It's important to make sure that all of the things are planar. So I actually use a book.
A physics book.
Yes, written by a friend of mine. Anyway, to make sure that this isn't twisted in here, these posts fit into the holders here, and you can tighten the screw here at a certain height, and I usually use a screwdriver to make sure that stays tight so it doesn't move on me. But then you can also loosen the screw here, and this is designed to go up and down smoothly, so you can adjust the height. Now, to get the height right, you need to have it at the center of the magnet. So you can go over and measure where the center of the magnet is using the meter stick. Yeah.
The PASCO aluminum meter stick.
Yes. The only one we have now. Yeah.
Here's a question. What's the typical accuracy / precision for the Bohr magneton experimental results?
I was just looking at that this morning, and I believe that it said around 1%. I was just looking at the manual to see what it said about that.
Yeah, we were talking about the height.
Yeah, right. And so once you know the height of the magnet from the table, then you can go over and find the height to the center of these. They have little marks on the center. So you can make everything aligned. So make sure everything is square, make sure everything is aligned in the same height. And what I find is that if there is a blurriness, or if it's not evenly lit, the first thing you can do is adjust the lens. You can move the lens back and forth, and you can tip it back and forth in order to make the illumination centered in that ring pattern. And then I find that if you align everything nicely, usually none of it is blurry. But if it turns out you do have a blurry spot in your pattern, rotate, you can loosen this, and you can rotate the etalon so that the interferometer gets rotated around, and it will show you if that blurry spot is moving on you when you rotate this. That's due to the fact that the etalons are not parallel enough. Then you need to start fiddling with these knobs. Two things about fiddling with the knobs, though. One is we recommend that you take a pencil and make a little vertical mark on where the knobs currently are, so that if you want, you can get back to where you were originally, because it's hard to remember how many times you've turned it. You don't have to turn them very far, and that's the mistake people make. They start cranking them down, and it gets all out of alignment. The other thing is you don't want to unscrew them all the way, because then it will pop off, and then you have to put it back together. But that's possible to do.
Brett, do we have a question?
Here's another question, Ann. Are the electron transitions from P to S states or S to P states?
It's from an S up here to a P down lower. So you're switching the, it is kind of upside down from what you think. Another question?
Nope.
Okay.
All right. Well, thank you guys for joining us for this Zeeman effect experiment. Yeah, and then we have a few more lined up for you today. So what's next after this?
Educational spectrophotometer.
All right, we have educational spectrophotometer next.